As you gaze into the vastness of space and take in the dazzling dance of stars, each of the billions of stars appears to raise a silent question that has plagued humanity for generations. Are we alone in the cosmos? Now, a groundbreaking instrument has been launched into orbit, the James Webb Space Telescope. This technological marvel works like a powerful magnifying glass, offering unprecedented clarity in revealing the intricate details of distant planets. Recently, the JWST set its sights on a remarkable target, K2-18b, an enigmatic exoplanet. Initial observations sparked a wave of excitement within the scientific community. This celestial body was no normal world. Not only did K2-18b exhibit the presence of water vapor, a potential indicator of habitability, but it also contained a molecule that sparked a lot of curiosity, one often associated with biological processes on Earth. Could this be the momentous revelation humanity has been waiting for, the announcement of extraterrestrial life? In this video, we'll go into more detail about K2-18b, exploring the scientific challenges and far-reaching implications that could reshape our understanding of the universe. Let's embark on an investigation of the first tangible image of K2-18b, located 120 light-years away. K2-18b is classified as a super-Earth and is considered a sub-Neptune, a category of planet unlike anything in our solar system. It is larger than Earth but smaller than Neptune, defying conventional planetary categories. This unique status provides a significant challenge for scientists attempting to understand its nature. While rocky planets like Earth and Mars serve as benchmarks for hypothesis building, gas giants like Jupiter, and further away, Saturn, offer only tentative comparisons. Sub-Neptunes, which have no familiar counterparts in our cosmic neighborhood, remain an enigma. Current data suggests fascinating theories. K2-18b orbits within the habitable zone of its host star, a red dwarf called K2-18, raising the possibility that its surface could harbor liquid water similar to the oceans of Earth. It's important to note that K2-18b's orbit is much closer to its star than Earth is to the Sun. While 1 astronomical unit, AU, represents the average distance from Earth to the Sun, K2-18b is only 18 cents away, closer than Mercury. As a result, a year on K2-18b only lasts 13 days on Earth. But thankfully, its red dwarf produces much less heat than our Sun. This prevents the planet's surface from being scorched and has allowed scientists to detect vaporized water in its atmosphere, a groundbreaking discovery that hints at biological signatures similar to those found on Earth. This discovery further elevates scientific interest in the planet. In addition to water vapor, the James Webb Space Telescope also detected methane and carbon dioxide in K2-18b's atmosphere. Methane, in particular, decomposes quickly under solar radiation, making its detection especially exciting. The possibility was even more fascinating: the presence of dimethyl sulfide, DMS, a molecule known to be produced almost exclusively by biological processes on Earth, primarily by microorganisms in the oceans. DMS is considered a reliable biomarker if detected in a planetary atmosphere. Given that K2-18b orbits a red dwarf known for its intense radiation, typically seen as inhospitable to life, the presence of DMS would be highly significant. If confirmed, it could provide a strong indication that life, at least microbial, might exist beyond Earth. For such conditions to support life, the planet must receive a manageable level of radiation and reside within a zone where temperatures are just right for liquid water to exist. Provided that K2-18b has a stable atmosphere, it could have Earth-like temperatures. However, its hydrogen-rich atmosphere would make its oceans slightly warmer than those on Earth. The close proximity between the planet and its star may help prevent surface water from evaporating entirely, an essential detail, considering new research suggesting that surface water may be a defining feature of Hycean, ocean-covered exoplanets like K2-18b. In 2021, astrophysicist Niku Madhusudhan proposed a new class of exoplanets called Hycean worlds, described in a paper published in the Journal of Astrophysics. These worlds are thought to be sub-Neptunes with a thick hydrogen-rich atmosphere and potentially vast oceans beneath. Hycean planets could be up to 10 times the mass of Earth and twice its radius. Though they may reach around 200 degrees Celsius, they wouldn't be boiling infernos. What defines them is a colossal ocean layer, possibly comprising up to 90% of the planet's mass. In theory, this vast ocean could provide the ingredients necessary for microbial life. Their dense atmospheres can trap heat from the star, allowing water to remain liquid over a broader range of distances than on rocky planets like Earth. Since larger planets are easier to detect with telescopes, Hycean worlds are prime candidates in the search for life. Dr. Madhusudan's team continues to study K2-18b using the James Webb Telescope. However, even with such advanced technology, detecting ocean worlds remains extremely difficult. The key to uncovering K2-18b's secrets lies in a meticulously planned approach to observation that calls for 5 total hours of data collection, split into 2 separate periods. K2-18b played a crucial role during a transit event, when the planet passed directly between Earth and its parent star. During this transit, the James Webb Telescope captured light filtering through the planet's atmosphere. The beauty of this technique lies in the spectral fingerprint that starlight carries. When a planet is illuminated by starlight, its atmosphere interacts with molecules, leaving behind a signature that scientists can read. By breaking down and separating this light into distinct wavelengths, like how a prism creates a rainbow, researchers are able to decipher the composition of the planet's atmosphere. By analyzing these spectral fingerprints, scientists can identify the gases present in K2-18b's atmosphere, and potentially infer signs of life. However, interpreting this data is no simple task. The signals are faint, and distinguishing between biological and non-biological sources of these molecules requires careful scrutiny. For example, while dimethyl sulfide, DMS, is a strong biosignature on Earth, scientists must be cautious. There could be unknown geological or chemical processes on K2-18b that might also produce it. Still, the presence of water vapor, methane, carbon dioxide, and the possible detection of DMS is an extraordinary combination. Each of these elements on its own might not be conclusive, but together, they form a compelling narrative, one that suggests K2-18b may possess the necessary ingredients for life. Moreover, the fact that these signatures were detected in just a few hours of observation underscores the power of the James Webb Space Telescope. With more time and targeted studies, researchers hope to confirm these findings and expand our understanding of this mysterious world. If future observations validate the presence of DMS and confirm that its source is biological, it would mark one of the most significant discoveries in human history. The confirmation of life beyond Earth, even if only microbial, would revolutionize biology, philosophy, and our understanding of our place in the cosmos. The implications would be far-reaching. Questions would arise: how common is life in the universe? Could complex life also exist elsewhere? Might intelligent civilizations be out there, watching the same stars we do? K2-18b has become a focal point for these questions, a symbol of our deepening exploration of the universe and our growing technological capability to seek answers beyond our solar system. As the James Webb Space Telescope continues its mission, the data it collects will not only inform scientists but also inspire humanity to look up and wonder. This is just the beginning. Specific molecules present in the atmosphere, if certain wavelengths are missing, provide vital clues about the chemical makeup of the planet, enabling a fuller picture of its environment. Let me know what you think in the comments box. If you liked the video, remember to like, subscribe, and share it to reach more people. Thank you so much for watching, and I'll see you in the next video. Imagine a world where the boundaries between science fiction and reality blur, a planet located 124 light-years away, encircling a red dwarf star in the Leo constellation. This is K2-18b, a sub-Neptune exoplanet that has become the focal point of astronomical research and public interest. K2-18b is classified as a Hycean world, a term coined to describe planets that are larger than Earth and covered by vast oceanic atmospheres. These characteristics make Hycean planets prime candidates in the search for extraterrestrial life, as their thick atmospheres are more amenable to detection by telescopes like the James Webb Space Telescope, JWST. Launched with the mission to peer deeper than ever into the universe, the JWST has provided unprecedented insights into distant worlds. Its advanced instruments have enabled scientists to analyze the atmospheric composition of exoplanets with remarkable detail. In the case of K2-18b, the observations made by the JWST have revealed the presence of methane and carbon dioxide in its atmosphere. These gases, when found together in certain ratios, can indicate the potential for biological processes, as they are commonly associated with life on Earth. However, it is essential to keep in mind that such chemical signatures can also arise from non-biological processes, necessitating further investigation. Perhaps the most intriguing discovery is the potential detection of dimethyl sulfide, DMS, in K2-18b's atmosphere. On Earth, DMS is predominantly produced by marine microorganisms, making its presence a compelling candidate for a biosignature. The detection of DMS in such high concentrations, thousands of times greater than on Earth, adds both excitement and mystery to the findings. However, scientists approach this discovery with caution. The statistical significance of the DMS signal is currently at a 3 sigma level, which, while promising, is not yet conclusive. In addition, the possibility of non-biological processes producing DMS cannot be ruled out entirely. Therefore, additional observations and analyses are essential to confirm these findings and fully understand their implications. The potential detection of DMS on K2-18b represents a significant milestone in the quest to answer one of humanity's most profound questions: are we alone in the universe? While this discovery does not confirm the existence of extraterrestrial life, it opens new avenues for research and exploration. The study of Hycean planets like K2-18b could revolutionize our understanding of habitability and the conditions under which life might arise. As technology advances and our observational capabilities improve, the possibility of finding evidence of life on distant exoplanets becomes increasingly tangible. The journey to learn the secrets of K2-18b is just beginning. Future missions, both from Earth and space-based observatories, will continue monitoring this enigmatic world. With each observation, we move closer to understanding the complexities of planetary systems beyond our own, and the potential for life elsewhere in the cosmos. As we stand on the precipice of these discoveries, one thing is certain: the universe is far more mysterious and wondrous than we ever imagined. With the discovery of promising atmospheric markers on K2-18b, scientists are now rethinking the criteria for planetary habitability. Traditionally, the search for life has focused on Earth-like planets orbiting within the habitable zone, where liquid water can exist on the surface. But K2-18b challenges this paradigm. Despite being a sub-Neptune with a thick hydrogen-rich atmosphere and potentially no solid surface, it still shows signs that could point to biological activity. This shifts the focus of astrobiological research toward a broader range of worlds. The concept of life itself may be far more adaptable than we previously believed. What if life doesn't require Earth-like conditions? What if it can thrive in deep oceans beneath dense gaseous envelopes, shielded from harmful radiation and driven by energy sources unfamiliar to us? To explore these questions, new missions are in development. Future telescopes like the Nancy Grace Roman Space Telescope and the European Extremely Large Telescope, ELT, aim to observe exoplanets with even higher precision. These instruments will allow scientists to analyze not only chemical compositions but also temperature profiles, cloud dynamics, and even potential seasonal changes in alien atmospheres. K2-18b may be just the beginning. It serves as a gateway to a new class of exoplanets, those that defy our assumptions yet hint at profound possibilities. The detection of molecules like DMS, methane, and carbon dioxide is not just data. It's a message from the cosmos, whispering that we may not be alone. This journey requires patience, skepticism, and above all, imagination. Each discovery builds upon the last, pushing the boundaries of our understanding and challenging our definitions of life. We are living in a golden age of exploration, not of continents, but of planets, stars, and the very fabric of the universe itself. As we continue to unlock the secrets of K2-18b and worlds like it, we are also redefining what it means to be human. For in seeking others, we inevitably discover more about ourselves, our resilience, our curiosity, and our place in the grand cosmic story.